To how many different ways you can stop a motor? There are two main ways. You can apply mechanical braking on a motor that is rotating, or actually there are three different ways. You can just remove the electrical supply and let the motor slow down by itself from the friction. You can apply mechanical braking, and you can apply electrical braking. So three methods that you can stop the motor. The first one, of course, you're not doing anything. You're just letting friction do the work, and it can take hours, if especially if it has a lot of inertia. If your load is heavy and it has a lot of inertia, if you just remove the power supply, then it may take hours and hours before it will finally stop. Electrical and mechanical braking are two main methods. Mechanical braking, of course, like in your cars, you apply actual physical mechanical brakes to stop the motor. And there are disadvantages of that, of course. A lot of heat can be generated, armature can get damaged, and all those things. But again, that's a method that is used. The method that is used most commonly is electrical braking system. And even in cars and stuff, electrical braking system is very common under regenerative braking. And as we discussed earlier, under Ward-Leonard system, when you change the direction of current through the motor, then the direction of torque become opposite, direction of force and direction of torque become opposite, and that starts slowing down the motor. That is electrical braking. So basically the idea is, if a motor is rotating in the counterclockwise direction, current is entering from one side of the motor in the armature. If you change the direction of that current, whichever way you want, the whole idea is change the direction of the current that is flowing through the armature. As soon as the direction of the current is changed, your force, Lorentz force, as well as the torque applied on the armature is going to be in the opposite direction, opposite to the direction of rotation. And when you are applying a force in the opposite direction, of course, it starts slowing the motor down. Now it is no longer applying the force in the same direction. And when it starts slowing the motor down, basically that's the electrical braking. It is possible that the motor is going to be stopped, or it is also possible that based on how you are supplying the current in the opposite direction, if you just let it supply even after it is stopped, then it is possible it will start rotating in the opposite direction. So but the basic idea again is, to stop a motor using electrical braking, you have to supply current in the direction opposite to the rotation of motor. That will apply opposite force on the armature as well as opposite torque on the armature. That will start slowing it down, and eventually it will stop it. There are two schemes that are discussed: dynamic braking and plugging. Look at the scheme of dynamic braking. So you have you have a shunt motor right here, and these are two arms, and you have a braking resistor. This is what we call braking resistor. So right now motor is running, and then you decide that you want to stop the motor. So you release the arms, in figure B, you release the arm and you connect the arm to the braking resistor. So now voltage is induced over here, right? Whatever voltage was here before you released the arm, that voltage is going to stay over here. And when you connect this to the braking resistor, now this motor is going to become a generator, and it will start supplying current to the resistor. And when it will start supplying current to the resistor, now what is the direction of the current? Direction is from top to bottom, and here the direction is from bottom to top. Hence that the torque that will be applied is going to be in the opposite direction. That will start slowing down the motor, and eventually when all the energy is going to be dissipated through this braking resistor, the motor is going to stop. In this case, we don't have to worry about that motor will start rotating in the opposite direction, because again, the power that is coming to stop the motor is the power that is being developed induced in the armature itself. There is no external power supply. So this is dynamic braking. How fast it's going to take to stop based on the time constant of the circuit. The smaller the time constant, it is going to stop faster. The larger the time constant, it is going to take more time to stop. Now many times if we are assuming that there is a resistance over here, armature resistance, then make sure you also assume this armature resistance over here. So the total resistance in the path of the flow of current will be this armature resistance and this braking resistance. And your total power, the braking power, is simply E naught times I2. That's your braking power at any instant of time, whatever the value of E naught at that instant of time and the value of I2 at that instant of time. Next is plugging, and the concept is same. That is, you're changing the direction of current through the armature, but the orientation is different, the arrangement is different. So basically, now you have those arms connected to the power supply of a shunt motor in this arrangement, and then you have a braking resistor connected on the other side, and the braking resistor is also connected to the supply voltage, like you see. Oh, not the braking resistor is connected to the supply voltage. It is basically connected, the ES is connected to the armature and through the braking resistor as well. Yeah. So what happens, it is running, and then once you want to change the direction of motion, direction of current, you remove the arm, you put the arm here, as you see over here, you put the arms here. So now the positive side of the source, which was connected previously to the top of R0, now this positive side is going to go through the braking resistor and it will be connected to the bottom of E0, and the negative side is going to be connected to the top of R0, right? So now the current that will flow through the armature is in the opposite direction. So it's going to go from here, it's going to go here, and then this will be I2. So thus the direction of current will be changed, and once the direction of current is opposite, it's going to start applying opposite force on the armature, hence opposite torque, and hence it starts slowing down. And remember, this is coming from ES, it's not coming from E0, this current. So this current value is usually higher than what it was before if it would not be ES. So it will start slowing down, and as soon as it will stop, if you don't release the arms, then of course the current will start flowing and then it start rotating in the opposite direction. So there has to be a mechanism where as soon as it will stop, you release these arms and no current will flow in the circuit. So this is plugging. If you compare coasting, that is, you just remove the power supply, dynamic braking, and plugging, you can see that plugging is the most efficient. It will stop the motor in the smallest amount of time. T0 is the time constant. Dynamic braking is the second, of course, and coasting may take a very long time. This example 5. This is a new example. It was not in the notes before, but make sure you go over example 5.5. And the next two topics, armature reaction. We discussed the armature reaction in generators. The same thing in motors. Armature reaction is, remember, when your commutator segments are shorted out by the winding, because those windings have induced voltage due to the fact that your neutral zone is misaligned now. And due to the armature reaction, you have sparking at the brushes, you have less voltage induced. In motors, that was in generators. In motors, it's the same thing, but in motors, of course, what do you have when the neutral zone is moved? The total flux pattern is changed, and when the total flux pattern is changed, you may have the motor speed up or it will slow down based on the new flux pattern. So again, it is important that total flux pattern should not change, and again we use commutating poles as we did in DC generators to cancel the flux that is produced by the armature and only keep the flux that is produced by the field in the system. Motor efficiency is very easy to read to know what is the efficiency of the motor, as long as you know what is the output power and what is the input power. So the input power, remember, is the source voltage times source current, and the output power is the induced voltage, CEMF, times armature current. So if you know these two quantities, then the efficiency is output power over input power. Now remember that the difference between output power, the difference between input power and output power are the losses in the motor. So right now, what we are discussing, there can be two losses in the motor. In the next chapter, we're going to discuss more losses. But right now, the only two losses in the motor that can happen are the loss in the armature resistance and loss in the field resistance. Then there are other losses. There are frictional losses, there are iron losses, hysteresis and eddy current, miscellaneous losses. So some of the losses we're going to discuss in the next chapter. But if it is given to you that the only losses are, of course, in the armature and the field, or if it is given ignore the frictional losses and iron losses, then the only losses will be due to the current of flow in the conductors, and conductors are in the armature and in the field. And those losses can easily be calculated either taking the difference between the input power minus output power, or simply by I square times RA, the armature loss, and I square times RF, the field losses.